is the dense material which comprises most of the surface of our planet. Often carved into majestic shapes by wind, water, and ice, solid rock forms all of the mountains on the Earth. Rock lies under every valley, plain, and ocean in the world. What are rocks made of? To find out, we will examine a piece of granite. This granite specimen contains small crystals of different substances called minerals. Minerals have distinct chemical compositions and physical properties. To study and analyze the minerals in the granite, a thin section of the rock is prepared. Under normal microscope lighting, this very thin slice of granite appears nearly colorless and seems to contain a great many components. But with polarized light, only the three common minerals of granite, feldspar, quartz, and mica, are revealed. Many minerals are complex, which means they are made up of numerous chemical components. Few are found in a nearly pure or native form, such as these copper crystals. More commonly, copper is combined with other elements. These green veins of malachite are copper combined with carbon, oxygen, and hydrogen. The chemical composition of malachite may be expressed as copper carbonate hydroxide. Crystal structure, as well as chemistry, is a critical factor in mineral characterization. Here, a tiny speck of a mineral will be identified by a process called X-ray diffraction. This technique employs a special camera to record on film a pattern of X-ray lines scattered by the mineral. The scattering pattern is characteristic of the mineral being X-rayed. The new pattern on top is compared with the standard pattern of quartz. The two are obviously identical. X-ray diffraction shows that the mineral is quartz. The arrangement of atoms within the mineral determines crystal structure. Some arrangements are very simple and symmetrical, as in this cube-shaped crystal of the mineral fluorite. The atoms of other minerals may be arranged in more complex patterns, as in these six-sided calcite crystals. Most minerals occur in the form of crystals, regular, repeating arrays of atoms that grow in orderly arrangements which form the mineral's atomic structure. In their natural state, crystals may appear outwardly dull or intensely brilliant. Some may appear flawed with impurities. Others, like this franklinite crystal, are perfectly formed, almost as though fashioned by a gem cutter. Although certain minerals must be identified by means of laboratory analysis, others may be instantly recognized simply on the basis of physical properties, such as color. Some, like this crystal of spodumene, appear to change color when being rotated. But in many minerals, the color we see in large specimens may not be their true color. Only the powder of these black minerals will indicate their true color. A powder trace is produced by rubbing each mineral across a piece of unglazed tile in what is called a streak test. The test shows one mineral is actually reddish-brown, the other black. Hardness, another property, is tested by scratching. Talc, one of the softest minerals, is readily marked by a fingernail. A hardness scale ranging from 1, talc, to 10, diamond, is applied to all minerals. Calcite, with a hardness 3, is easily scratched by a piece of feldspar, having a hardness of 6. Diamond, with a hardness of 10, is the hardest of all minerals. Still, another physical property is luster. That is, the way light is reflected. Fibrous has the luster of silk, while this exceptional quartz crystal has a glassy luster. Luster is an important aid in mineral identification. Some minerals may be classified by the way they split or break apart. This property is called cleavage. Notice how this calcite crystal, when struck sharply with a hammer, shatters or cleaves into smaller pieces of similar rhomboid shapes like the original. Color, hardness, luster, and cleavage are physical properties that are very useful in identifying specimens of the approximately 3,000 minerals known to exist. Now, through photomicrography, we will observe the rapid growth of crystals. These crystals are growing in a solution under controlled laboratory conditions, and their colors induced by polarized light. In nature, crystal growth may occur this rapidly, but mineral crystals may grow exceedingly slowly, requiring hundreds of years or more for just one single crystal to form. Minerals are commonly found as crystals in caverns in limestone. This cave is lined with large crystals of celestine deposited from groundwater. Atom by atom, over many, many years, these crystals grew from tiny ones into their present giant size. Once groundwater carrying dissolved minerals flowed through the cave. Over a period of time, the mineral concentrations in the water increased to such a level that crystals began to grow within the cave. Eventually, the groundwater receded, leaving behind this impressive example of the slow growth of mineral crystals. Crystallization may occur much more rapidly on the Earth's surface. When volcanoes erupt, they throw off lava, which is hot liquid rock. The lava cools quickly, forming small mineral crystals that are locked together to form large rock masses. Mineral crystals also grow where hot gases and vapors escape from the Earth's interior. When vaporized sulfur in the gas comes in contact with cooler surfaces, like these rocks, yellow sulfur crystals begin to grow. Minerals are also dissolved in the waters of hot springs and geysers. They too will crystallize on cooler surfaces, creating unusual rock shapes. Scientists recognize three major groups of rocks. Rocks formed from lava created by volcanic action are one type of igneous rock. Other igneous rocks form beneath the Earth's surface. Sedimentary rock consists of fine rock particles, chemical precipitates, or organic materials that have been deposited in layers. Over thousands of years, these materials were buried and became solidified into rock. This is a metamorphic rock called gneiss. Metamorphic rocks were formed by recrystallization when the parent rock was deeply buried and subjected to extreme heat and pressure. Geologists study all of these rock types, as well as the minerals they contain. Some are of great economic value. At the Great Salt Lake in Utah, the mineral halite, or rock salt, is being processed in huge quantities. Here, salt water from the lake is spread in flat, shallow basins. The sun's energy evaporates the water, and salt crystallization occurs. The salt is then gathered with a specially designed equipment. The salt derived from the Great Salt Lake comes from an unusual surface mineral deposit. Other valuable mineral deposits are not so easily reached. For centuries, we have dug deep into the earth for ore, rock which contains commercial quantities of useful minerals. In some areas, concentrated mining has drastically reduced supplies of such ores. This open-pit copper mine at Bingham, Utah, is one of the largest in the world. The rock removed from the pit contains a variety of copper minerals. But recently, the ore has contained decreasing amounts of copper, and every year, larger and larger quantities of rock are required to produce the same amount of pure copper in the smelter. Copper ingots are still being produced here, but the supplies of this vital metal are becoming depleted. As deposits of many important minerals dwindle, conservation and recycling are of utmost importance. Many minerals are treasured for their beauty. This miner searches for the finest of the mineral kingdom, gemstones and unique mineral specimens. Few people make a living at this type of hand mining, for it is extremely tedious work and success is unpredictable. More often than not, a gem miner's effort is unrewarded because gems and large mineral crystals are very rare. Variscite occurs in large nodules or clumps, and a good specimen like this will find a ready market. Cut and polished, this nodule is an outstanding example of gem variscite. Even more valued are the products of the gem facitor, whose skill and artistry, precise polishing and fine cutting can create jewels of great beauty and value. Fine jewels like this flawless emerald are the masterworks of an art that requires perfection of both man and nature. The unique qualities of some of the world's greatest jewels, like the famous blue Hope diamond, have inspired both legend and greed over centuries. The Hope diamond is now a feature attraction of the United States National Museum of Natural History in Washington, D.C., a part of the Smithsonian Institution. The Smithsonian Gem and Mineral Collection contains some of the finest specimens that have ever been removed from the earth. Some minerals in the collection are used for scientific research by mineralogists. Others, because of their beauty and rarity, are on display in the museum. From the beginning of human history, minerals have been closely linked to the development of civilization. They have provided both rare beauty and the basic resources on which the world's industrial societies have been based. Knowledge gained from the study of minerals has greatly helped technology advance to its present state. The study of minerals and the investigation of crystal formation, growth, structure, and chemical composition continue to help scientists probe the secrets of the Earth and the entire solar system. Today, we know that the quality of life in the future will be determined in part by how we consume, conserve, and recycle this valuable treasure, our mineral resources.